Welcome to Building Material Testing Laboratory. Today we are going to conduct an experiment to determine the fineness modulus and grain size distribution of fine aggregates. To determine the fineness modulus and grain size distribution, you require apparatus such as IS test tubes of size 4.75 mm, 2.36 mm, 1.18 mm, 600 micron, 425 micron, 300 micron, 150 micron and 75 micron. Also, you require equipment such as weighing balance, sieve shakers, oven and trace. This is the pictorial representation of the sieve set. What is the procedure to determine the fineness modulus and grain size distribution of fine aggregates? Take 1 kg of sand or M sand from a laboratory sample of 10 kg by quartering and breaking clay lumps, if any, in a clean dry rice plate. Arrange the sieves in order of IS sieve numbers, that is 4.75 at the top, forwarded by 2.36, 1.18, 600 micron, 425 up to 75 micron. Fix them in the sieve shaking machine with the pan at the bottom and cover at the top. Place 1000 grams of M sand sample on the top sieve. Carry out sieving in the set of sieves as arranged before for not less than 10 minutes. Find the mass retained on each sieve. Then, fineness modulus is an empirical factor which is obtained by dividing the cumulative sum of percentage of aggregate retained on each IS sieves taken in order by 100. Some of the observation and calculation. It is very important to note down the mass retained on each sieve starting from 4.75 mm up to the pan. Fineness modulus of fine aggregates is equal to sum of cumulative weight retained divided by 100. After calculating the cumulative percentage and percentage finer, a similar graph sheet is plotted in which in the x-axis the particle size, against the y-axis the percentage finer. Similar graph is used and percentage passing is taken in the ordinary scale and IS sieve size on the logarithmic scale. For the conduction of the sieve analysis, make sure the sieves are arranged in the decreasing order of their size, that is 4.75 mm sieve at the top, 2.36, 1.18 mm, 600 micron, 425 micron, 300 micron, 150 micron, 75 micron and below 75 micron. Make sure that the pan is attached to the sieve set. For the conduction of the sieve analysis test, measure 1 kg of fine aggregates and fill that fine aggregate in the sieve set. Exactly take 1 kg or 1000 gram of fine aggregates for the conduction of sieve analysis. Pour the fine aggregate on the 7.5 mm sieve set and keep the entire sieve set on the sieve shaker by closing the lid of the 4.75 mm sieve. The fine aggregates is filled to the sieve set and make sure at the top the lid is closed and place this sieve set into the sieve shaker and subject it for a 5 to 10 minutes of shaking. The sieve set is placed on the sieve shaker and this will be subjected to 5 to 10 minutes of shaking. After the sieve shaking, measure the mass retained of fine aggregate on each sieve size. In this picture, the weight that is showing indicates the mass of fine aggregates retained on the sieve size 2.36 mm. Similarly, measure all the mass of fine aggregates retained on all the sieve sizes which was used for the conduction of the experiments. Now let us come to the very important part related to this particular experiment, that is the calculation. The first two columns indicates the sieve size and the second column indicates the mass retained on each sieve. In terms of 4.75 mm, the mass retained is 0 gram. In terms of 2.36 mm, the mass retained is 6.5 gram. In terms of 1.18 mm sieve, the mass retained is 261.5 gram. And in 600 micron sieve, the mass retained is 163.5 gram. In 425 micron sieve, the mass retained is 49.5 gram. In 300 micron sieve, the mass retained is 25.5 gram. In 150 micron sieve, the mass retained is 389.5 gram. And in 75 micron, the mass retained is 65 micron. And in the receiver pack, the mass retained is 22.5 gram. If you sum it up, the mass retained you are going to get is 983.5 grams. If you remember, at the starting of the experiment, the total mass taken was 1000 gram. There is almost 16.5 gram of loss which is related to dust. Now, a very important calculation that is related to corrected mass retained. So, in terms of corrected mass retained, we have to distribute 39 grams of fine aggregates from 4.75 mm to 75 micron. Now, where does this 39 grams comes into the picture? If you look into the tabular column, there is 22.5 grams of sample which has been retained on pan, and there is 16.5 grams of soil which has been lost due to dust. So, this 16.5 plus 22.5 gram indicates 39 grams. So, therefore, if you look at this particular tabular column, overall mass to be redistributed is 961, that is 39 grams. Now, how to calculate the corrected mass? That is, corrected mass is equal to mass retained divided by total mass multiplied by total mass taken. Now, let us simplify that. Corrected mass for 4.75 mm sieve. What is the mass retained? 0 divided by what is the total mass actually calculated, that is 961 gram, multiplied by what was the total gram taken, 1000 gram. So 0 divided by 961 multiplied by 1000 gives us 0. Now let us look into 2.36 sieve. What was the mass retained on it? It was 6.5 gram. How that this value 6.76 came? That is 6.5 divided by 961 multiplied by 1000 gives us 6.76 grams. That means there is an increase of 0.26 gram. That is 39 grams has been redistributed of amount 0.26 to 2.36 mm sieve. Similarly, let us look into the calculation of 1.18 mm sieve. Here, this 272.11, how does this value came? It is 261.5 divided by 961 multiplied by 1000 gave us the value 272.11. Similarly, for all the sieves starting from 4.75 mm up to 75 micron is recalculated, and if you sum it up, the total mass that we are going to get is 1000 gram, which was initially taken. So this correction is very important in terms of sieve analysis, and also considering the dust, the loss that happened, and also the mass that was present in receiver pan has to be redistributed correctly. Now let us come into this particular tabular column, percentage mass retained. What is the formula to calculate the percentage mass retained? The formula to calculate percentage mass retained is equal to corrected mass divided by total sample taken multiplied by 100. That is, Corrected mass for 4.75 was 0, divided by total mass was 1000, multiplied by 100 gives us 0. Let us look into the calculation of 2.36 Sieve. Corrected mass is 6.76, total mass taken was 1000, therefore 6.76 divided by 1000 multiplied by 100 gives you a value of 0.68%. Let us take 1.18 mm Sieve. 272.11 is the corrected mass retained, therefore percentage mass retained is equal to 272.11 divided by 1000 multiplied by 100 gives you the value of 27.21. Similarly, calculate the percentage mass retained for all the sieve sizes starting from 4.75 up to 75 micron. Let us look at the cumulative percentage retained. For 4.75 it is 0. For 2.36, 0.68. For 1.18 if you observe, it is 27.89. How does this value 27.89 came? 27.21 plus 0.68 gives you 27.89. Similarly, for 600 micron, how does this value 44.90 came? It is 27.89 plus 17.01 is equal to 44.90. Similarly, for 425 micron, 44.90 plus 5.15 gave you a value of 50.05. Similarly, 300 micron, 50.05 plus 265 gave you a value of 52.71. For 150 micron, 52.71 plus 40.53 is equal to 93.25. For 75 micron, 93.24 plus 6.76 gives you a value of 100. There are two ways in which the experiment is going to be determined it is correct. One is the corrected mass has to be 1000 and the cumulative percentage retained for 75 micron is 100. Now let us come to the last tabular column, that is the percentage finer. How do you calculate percentage finer? 100 minus cumulative percentage retained, that is 100 minus 0, 100, 100 minus 0.68, 99.32, 100 minus 27.89, 72.11, 100 minus 44.90, 55.10, 100 minus 50.05, 49.95, 100 minus 52.71, 47.29, 100 minus 93.24, 6.76, 100 minus 100, 0. What does the meaning of this percentage finer indicates? That means 4.75, there is 100% of particles which is finer than 4.75. What is the meaning? 2.36 is equal to 99.32. That means 99.32% of particles are finer than 2.36. Similarly, with respect to 1.18 mm, 72.11 particles are percent finer than 1.18. Similarly, if the calculation is correct, for the 75 micron, the percentage finer will be 0. Using this percentage finer with respect to y-axis and particle size in the x-axis, plot a semi-log graph sheet, and based on the curve you are going to get, whether it is a S curve or a non-S curve, then the soil can be classified as well graded, uniformly graded or poor graded. Thank you.